Morning everyone. Am I audible to you guys? Okay. Okay. Only 7 students. Okay, so today we will see two types of graph traversing algorithms. Okay. So what is traversing? If I say traversing means what? What do you understand by traversing? Any guesses? Traversing the graph means what? Any idea? Any idea what is graph traversing? If I say I'm going to traverse the graph, what's the general meaning of that? Searching, okay. Okay, tell me if I tell you like I'm going to travel to maybe Shillong. Okay, I'm going to travel Shillong and I have like certain viewpoints in my mind. So I'm going to just travel or visit all those viewpoints. Okay, so what I have to do that? Moving stepwise to the destination. Yes, that's correct. So if I say I'm going to travel to some place and I want to just visit most of the viewpoints, I'll just follow the paths, right? I'll obviously follow the road to which I can just reach the viewpoints. Okay, so graph traversing means it's a process or examining that all nodes and vertices of the graph. Okay, so traversing is same for both graph and tree data structure. Remember, tree is also kind of graph, a graph without any self loop. Okay, so traversing the graph means examining or visiting all the nodes and the vertices and the edges of the graph. Okay, and there are two standard methods for traversing a graph. One is depth first search and other is breadth first search. Okay, this is a searching algorithm, but mainly it's like I'm going to explore all the nodes in a graph or all the nodes in a tree. Okay, so two types.
नहीं सामने ये अलग बात है नहीं ये अलग बात
Someone
निकला
singing.
जाती
Who is singing? Who is singing? Who is singing? This is not your music class, so if you want to sing, you can just leave the class and just sing. Okay? Anyway, so there are two types of graph traversal. One is depth first search, and other is breadth first. So what happens in depth first search? So depth first search is the recursive algorithm for searching all the vertices of a graph or a tree data structure. So whenever we do a searching, what we do, we just start from a initial node and then we just goes deeper and deeper until we find the node we are looking for, or until we get a node which does not have any children. That is mainly in case of both tree and graph. Then once you reach the leaf node, then you will just backtrack from the dead ends or any node which is yet to be explored completely. Okay, so to remember all the vertices that you have traveled during your depth process, we use a stack. Okay, stack data structure is used to remember all the vertices that you have visited when you do a depth first search. Okay, so if I say in case of tree, it will be like, suppose this is a tree, this is a tree. So the name is depth first. That means you will go deep. Okay, you will go deeper into the tree, then you will backtrack one by one. So first, this is your source node. So from source node or initial node, you will start traversing. So first you will go to the next level. Okay, then you will go again to the next level, whatever will be the subtree for that particular node. Again you will go deep and deep. So this is your leaf node, and it's a leaf node, and you can, there is no nodes after this. So since you have reached a leaf node, so you will go back. So once you reach D, you will go back to, you will go back to B. So you will go back to B. So B is still an unexplored node, which is E. So from B, that means this is already visited, you will come to E. Okay, once you reach E, then E is again your a leaf node. That means for the B, all the subtrees or children are explored. So you will go back again. So from B, you will move to A. A has one um, node left, which is C. So you will come to the C part. From C again you will go deep. Okay. So this is your leaf node. So once you reach this node, that means the left subtree is already visited. So once you are done with the left subtree, then you will again go back to the source node, because this source node has another like right subtree which is still yet you need to explore, right? So after reaching means G, it will go back to, let's not get written. You, it will go back to S, then from S it will again start doing the same thing. That means it will reach H, then after that it will go to I, then will come to K, then since K is the leaf node, again will go back, then will come to J. So this is DFS in tree. Remember in tree we also learned about three types of traversing: in order, pre-order and post-order. So that is also a type of DFS in case of tree. So those three types, pre, in order and post order, are types of DFS in case of tree. Okay, in tree, those are depth first search. That means we will go deeper to the tree, then we will backtrack and we'll check if there are any unexplored nodes. Okay, now same concept is also for the graph. So if this is a graph, first this is, it's not getting written. DFS, you will start from S. From S, you will come to A. Okay, from A, you, what are the adjacent nodes for S? It's A, B, and C. Okay, in depth first search, I'll come to node A first. You can also select B or C. It's up to you, not a problem. So just think I'm just going alphabetically. So I just visited the node A first. Okay, once I visited node A, I will again check if there is any node or adjacent node connected to A. So there is a node connected to A which is D. So I'll visit D now. Okay. Again I'll do the same thing. I'll check if there are any adjacent node to D. So D has a adjacent node and which is G. Just a minute. Okay, just leave it. G. So now from G, there are two adjacent nodes E, F, correct? D is already visited, so you have two options. Either you can go to E or you can go to F. In this case, I'm just following the alphabetic order, so I'll just go to E first. Okay, from E, again I'll check if there is any adjacent node. Okay. You can also go to F, not a problem. Just that once you reach C, then you again have to come back. Okay, in this case, I just visited E first. Then E has a adjacent node which is B. Okay, so after reaching B, there is one adjacent node which is S, and S you have already visited. So you will backtrack again, come to G again. Signature, Adi loy ba? Okay, so S is already visited, so you will just backtrack. Okay, after backtracking, you will come to G. From G, again there is one adjacent node which you have not explored before, so you will visit F. Then again from F, there is one adjacent node C. Then from C, one adjacent node which is S, but this one is our starting point, so our graph traversal ends here. I'm not sure what I'm not able to write today. So anyway, so what we do, okay, let's just see example from my side. Okay, it will be easier. So I'll see the depth first search first. So suppose these are our node. Let's take a bit complicated one. হা মই ক্লাছ কৰি আছো ৰবা I'm taking a bit complicated graph so that when I give a bit easier, it will be easy for you guys. Okay, so this is the graph we need to travel. Okay, we are going to do a DFS here. Okay, remember for DFS, we remember all our visited nodes with the help of a stack. So we will maintain a stack here. Okay, so here I am going to put all the visited nodes. So first, suppose I am going to start from A. Okay, so I am going to start from A. I'll just write A here. Okay, I'll just push A here. So I can say this node is visited. Okay, next I have two adjacent nodes. One is B and one is S. Okay, so suppose I am choosing this one first. So I'm going to visit this one. So I will push B here and shade it because I have visited B now. Okay, now B does not have any adjacent nodes. So what I have to do? I have to go back to A again. Okay, now A has another adjacent nodes. So I will visit S now. So B does not have anything. So I am going to pop this up. Okay, B does not have any um, nodes, adjacent nodes. So I am going to pop this B. Then I am going to visit S. I'm going to visit S. Okay, because this is a dead end. So I'm going to pop it out. Okay. Now from S again I have two adjacent nodes C and G. So I'll just go to C first. Okay. So from C I'm going to push it onto the stack and visit C now. Okay. From D again, C again I have D, E, F. I'm just following the alphabetic order. Here you can do one thing. Whenever you push things, you can write the output here. Okay. So first I visited A, right? So output also you can write A and you push it A here. Then next you visited B and you inserted B here first. Remember B does not have any node, so you just popped it out. Next was S. Okay. So I push S here. So in the output also I will just write S. Okay. Now from S I went to C, correct? So in the stack you are going to push the C here. Then after that you have to write it here as well because you have just visited C. Okay. From C you have three adjacent nodes D, E and F. So I'm just following alphabetic same thing. So I'm going to visit D. So I'm just going to push D here. Okay. Now I can say I have visited D. Okay. Now D does not have anything. It does not have any adjacent nodes. Correct. I visited D, write D here. So I'm going to pop this D now. Okay. Because this is the dead end, I'm going to pop it now. Next, I'll come back to C again. Okay. I'll come back to C again. From C, now I want to go to E. Okay, so E, I'll push it here, and I have also visited E, so I'll just shade it. Okay, from E, what happened? From E, have one adjacent nodes, right, which is H. Okay, so I'm going to push H here. E, from here I'm going to H, so I have also visited H, so I'm going to write H here. Okay, from H I have another adjacent node which is G, so I'm going to add G here, also write G here in the output. Okay, from G I'm going to visit F, there is only one adjacent node. Okay, so finally I put push F inside here and also written visited here. Okay, now the thing is, from F there's only one node, correct, and C is already visited. Okay, since it's already visited, that means this is a dead end, so I'm just going to pop out this F. Okay, so after that, once it's done, you can just popping out all the items in a stack one by one, then in the end it will be just empty stack. So once traversing is done, you can just pop these values, but final value is this one. Okay, this is your DFS. So in case of DFS, you will just go deeper and deeper. You will visit one node, then you will check if there is any adjacent node. Then you select one adjacent node, then again you check is there any other adjacent node or not. So whenever you will see a node visited, then you are going to push it onto the stack and you will also write in the output. Okay, the same steps I have written here as well. So start by putting any one of the graph's vertices onto the top of a stack. Then take the top item of the stack and add it to the visited list. Okay, so this output is just your visited list. Okay, output is nothing but your visited list. Then create a list of vertices of adjacent nodes, then add ones which are in the visited list on the top of the stack. Then keep repeating this whole thing over and over again. Okay, I have another example here. Okay, so in this example, this is a simple graph, very simple graph, only 5 nodes are there. So I'm just keeping one list for visited and one for the stack. So in this case, first I'll start from 0. Okay, so in 0 I just put in the visited list. Okay, then what are the adjacent nodes? In this case it's 1, 2 and 3. So in the stack I push 1, 2, 3. Okay, this is a bit different method because it also depends on the program you used. Okay, so just stick to 1 actually, just push 1. Okay, just this one you can check, it's fine. So from here you can go to 1, 2 and 3 is still in the stack, so next you are going to visit 2. Okay, so you just keep 2 in the visited list. From 2 you have one adjacent node which is 4, so you are going to push that node onto the top of the stack. So after that you will visit 4 and you will just keep in the adjacent visited list. So next last is the 3, then you will visit 3 and this is your empty stack. Okay, so I think this one might be a bit confusing, so just follow this method. So whenever you visit one, you keep it in the stack, then again keep it in the output. Is this clear? DFS. Okay, Hitachi said yes. Others, Gunnar said yes. Nitul, yes. And rest, Rohit, yes. Okay, good. So this is your DFS. Now what happens in breakfast? Okay. Okay, let's see in terms of tree first. Okay, let's. Okay, I'm just showing DFS first. Okay, so in case of DFS, you will go deep, deeper level. Then you will just check again. Okay, here. Then you will visit this. Once this part is done, then you again go up. Then again go down. Okay, this is your DFS. Now what happens in case of BFS is, if this is your tree, you are going to visit nodes level by level. That's why BFS is also said level order search. That means if you start from this node, first you are going to visit this level. So once you are done with the level 1, this is your level 0, this is 1, this is 2, and this is 3, right? So once you are done with traversing or visiting level 1 nodes, then only you will go down to the level 2 in the second step. Okay, this is your BFS. So once you are done with this level, then you will go to the level 3. Okay, that's the difference between DFS and BFS. Breakfast, you will go level by level. You can also see from the word too, it's breakfast. It can have any number of children, but it will be breakfast. Okay, bread. And it's depth first. It will go deeper in DFS, then will come up and again go deep. In case of BFS, it will be just level by level. Okay, first this one level will be search or visited, then second level, and then next level. Is this concept clear? BFS and DFS. I'll give you example for graph, but this is the basic logical concept. BFS will go level by level searching, and DFS will go to the deeper level as much as possible. So once it gets the leaf node, then it will go up again and check if there is any node unexplored. Okay. And in case of BFS, it will just done visiting all the nodes in the same level, then it will go to the deeper level. Without completing one level, it will not go down below level. Okay, so let's just take the same example actually. So let's, okay, I'm taking the same. is taking the same graph. You will see the difference. Okay, so I'm taking the same graph. Just remember, for the breadth we use a queue data structure. Okay, we use a queue. So I'm just drawing it in the same way. Just remember, in queue we NQ from one end and DQ from the other end. Okay, so here it's a queue data structure. And in case of DFS we use a stack. Okay, similarly here also we will maintain a visited list or output. Okay, so I'll start from A. So A is visited, I'm keeping it A. Okay, now from A I have, what is the adjacent node? It's B. I'm going to visit B first. So what I'm going to do, I'm not going to insert A. Instead, I'm going to insert B here first. Okay. From here, I'm going to insert, and from here, I'm going to delete. Okay. So B is visited. I'm going to write B here. So B is done. There is no adjacent node for B. So I'll backtrack again to A. Okay. So it's a level by level. Next node is S. So I'll visit node S and push it onto the stack. Okay. Since B was your last node and there is no adjacent node, I'm going to DQ this B. Okay, when I just return, B does not have anything, so I'll just pop out, not pop, it's called DQ from the queue. Okay, now these are done, so this level is done. Okay, from S we will go to the next level. Okay, so from S we have two adjacent nodes, one is C, correct, and one is D. Now I'm not going to go to D. I'll check all the nodes adjacent to S. So I'll visit only these two nodes. So first, suppose S is done, I can just DQ it. Now I can just DQ it from here. Next, I'm going to visit C, for example. So I just put it in C and I enqueued C here. I entered C here from here. Okay. Next, after visiting C, I will visit Z. So this is your output. So I'll enqueue G here. Okay. It's up to you. Okay. You can also visit G first or you can also visit C first. But if I say like alphabetic order, just following it like this. Okay. But there is no hard and fast rule. You can either visit this one or you can also visit this one. Main thing is you need to visit something. Okay, now I decided, because C is like in front, I will visit all the nodes which is adjacent to C. Okay, so since I'm going to explore the level, all the adjacent node for C, I'm going to DQ C now. Okay, now from C, what are the adjacent node? D, E and F, correct? So I will just enqueue D, E and F. Now I am going to only select the adjacent node for the C. What are the three nodes? D, E and F are adjacent to C. So I enqueued G, D and E. So now I'll visit, for example, D first. So here I'll write D. Okay, so here again backtrack, then again I will visit the next node E. Okay, then the other one is F, so I will visit F. So for C, all the adjacent nodes are visited. So now I'll come to G again. Now I'll explore the part from Z because I have traversed all the nodes from C. Now I'll come back to G again. That means I'm going to pop out this G now. Okay, from G there is only one adjacent node which is H. So I'll just visit H now. Okay, so it's done. So since all the nodes are, I will include H here. So these are already visited. So I can just dequeue the queue one by one. Okay, once done, you can just dequeue one by one. So this is your final. Okay, ma'am, row wise or column wise as per our row wise or column wise as per our Bisham bread because of such person. Means row wise, column wise, not the case. Just remember, if you have one node, you will visit all the adjacent nodes for that particular node first. Then only you will go to the next node. Suppose from A, I'll first visit both these nodes. Only after I'll check if other nodes have any other children or no. Okay, it's not exactly row wise and column wise. You cannot find out the row and column because it might not be in same because your graph can be like of any form. It can be like this also. Correct. It can be of any form. So in this form, you cannot say which one is row and which one is column. DFS uses tag, but BFS, yes, for DFS, uses tag to remember the visited nodes, and BFS uses queue to remember the visited nodes. That's the difference. And remember, for the depth firsters, what we do, suppose I'm just giving a simple example here. Okay, just giving a simple example. In case of DFS, okay, what I'll do, I'll first visit the initial node, correct? So after visiting that, I can go to any direction. Either you can visit this one or you can visit this one. It's up to you. Suppose you choose this one. Okay, so you will visit this one first. Okay, since it's DFS, you will go deeper. So from this node, you will again check if there is any adjacent node for that particular node or not. So from here, two nodes are adjacent. One is this one and other one is this one. So this one is already visited, so we don't care about the visited nodes. So unvisited node is this one. I'll come here. Okay, so from here again I will do the same thing. If there is any adjacent nodes, one is already visited, the next one is this one, so I'll visit this one. Again same thing, check the adjacent nodes, unvisited nodes. So this one already visited, this one unvisited. I will come here. From here you will see the adjacent nodes again unvisited. These two already visited, only unvisited node is this one. Okay, this is DFS. Suppose you are doing BFS, so what will happen, you will start from here. Okay, from BFS you will check what are the two adjacent nodes. So both this one and this one is your adjacent node to this. So first suppose you want to visit this node first. Okay, so after visiting node you cannot go to its adjacent node. Okay, you will finish all the adjacent nodes from the source node only. So after visiting this node you will visit this node. Okay, so after this again it's up to you, you want to explore this node or this node. If you want to explore this node, for example, you will visit here. Okay, for this particular node there is only one node, correct? So this one is done for this particular node. Then you will move to this node. For this node, again two nodes are there. You can either select this one or this one. Suppose I selected this one, then you come to this one. So DFS is more like you are just going from one point to one point, or one point and one point. If then you see there are different routes are there and you want to explore them too, then you again backtrack and see all the unexplored one. But for BFS, from one point you will see all the possible paths. You will finish all the possible paths or connected routes from that particular source. Then only finishing that only you will move to the other points. Okay. So for this node, again suppose you will explore this node first, then this one will go level by level and this one will go deep. Even we can use two stack instead of a queue DFS, it is possible, but it will consume more time and space. Yes, correct. Since it's a level by level, we have to keep track of that thing. Okay, that's why queue is used for BFS and stack is used for DFS. Is it clear for both DFS and DFS? Everyone? Is the concept clear? Okay, so you can say your BFS is better when your target is closer to the source, and DFS is better when the target is far from the source. Yes, both has advantages and disadvantages. So BFS will be beneficial when your target, it's mainly for searching, right? If your the target or the node you are looking for is closer to the source, then it's better you just go for the BFS, and if it is far from the source, then you have to BFS is better. Okay, then again, the BFS considers all the neighbors, so it is not exactly suitable for decision tree, and which is mainly used for your puzzle games. Okay, so DFS is more suitable for a decision tree. Okay, decision tree concept you will get in later stages, but it's kind of classifier for puzzle game, and those they use decision tree. It's a very important concept too, but this is not exactly like data structure. Decision tree is more like um, it's a rule based classifier. Okay, so BFS is suitable. Sorry, DFS is suitable for your DFS decision tree, and DFS is not. Again, if you see the speed, then you will see BFS is slower than DFS and DFS is faster. Okay, but the time complexity is same for both. Okay, for both cases, time complexity you can represent in terms of V plus E, where V is your vertices and E are edges, because of course it's traversing all the vertices and edges. So time complexity is just vertices plus edges. Here difference is clear. But yeah, the memory requirement is obviously a bit more than your DFS because DFS uses Q. And another advantage of DFS is that there is no backtracking is required. But in case of DFS, we need backtracking. Again, since it's DFS, you can also just tap into your infinite loops. If there is any loop in a graph, then it's possible that you will just stuck into that loop there if you use DFS. Okay, but in BFS, you will not just tap into the infinite loops. Okay, is it clear? Both concept BFS, DFS. So this is all about your syllabus. So your data structure and algorithm syllabus is finished. So from next class onwards, we will just keep revising all those units. Okay, if you have any doubt, you can ask me and all. And we will do more problem solving. I can just give tests and all. Okay. Okay. So I'm ending the meeting now. If you have any doubt, you can ask in the group, not a problem. Just remember the basic concept. If your concept is clear, doesn't matter how big is your graph and how complicated is your graph. If concept is clear, you can just visit all those things. And this traversing thing is also very important for a traveling salesman problem, which mainly comes in design and analysis of algorithm. And it will be in the next semester. But yeah, for the algorithm, there's a whole like subject for it, design and analysis of algorithm. So these same concepts will be applied in that particular um, subject. You will get it in next semester. Okay. Okay. So I'm just stop sharing. Others clear. Partha, Manish, Imam, Kiranjit, Lexi, Sordan, Tanmay, Tithankar, Dipu, Abdullah. DFS clear. Okay. Okay. Good. Okay. Okay. Very good. I can give homework then. Okay. Thank you, everyone. I'm just ending the meeting now.